All right, then I'm going to introduce our guests. You know that we had a little series of talks in the HPC Cafe about software development, starting with an introduction to Git and some advanced Git techniques. And today we have guest speakers from the Karlsruhe Institute of Technology, KIT, Jennifer Buchmüller and Terry Cojean, who will tell us about continuous integration, continuous benchmarking, and continuous deployment in an HPC environment. If you know HPC in Germany, you know that Karlsruhe has a long history of high-performance computing, running systems, developing software. So these guys know what they're talking about, and we are very much looking forward to your presentation, Jennifer and Terry. Go ahead.
Okay, thank you very much also for this kind introduction. So, add in full screen. Oh, perfect. Okay, so yeah, thank you very much also for the introduction to take part of this cafe, because also you mentioned in those COVID kind of days, having this interaction and also talk and discuss things without coffee in your hands getting pretty hard there, but I think it's good to have some kind of interaction there and to exchange your experiences. And also I think NHR, as we started or getting started in Germany, I'm quite happy that sustainable software development is a very important topic. It was the topic not only from KIT, but also colleagues from Erlangen. We have this very strong point in common. And I'm happy that we have one project. We named it Continuous X, as it stands for continuous integration, deployment, testing, but also benchmarking HPC systems. So in the next 50 minutes, I will give you a rough tour what we have done so far at KIT, and we want extend it in NHR. And on this very first slide, you can see some glances of our new tier 2 system, Eureka, that is currently set up. And we, fingers crossed, we hope to get there in the top 10 of Europe, in the top 500 in the next couple of days. So we will see how that goes. Some words about myself. I'm head of the department and the HPC core facility leader in the scope of NHR, but also at KIT we have a tier 3 system. And my department is also responsible for software packages and scientific operations. But from my point of view, one of our key focus topics is performance optimization as well as sustainable software development. And here you can again see the strong point of continuous testing, integration and deployment as a service, so that we are able to set up an infrastructure that every scientist can use from the very beginning, but also to the other edge of a very experienced user. If you have a large community code, for example, that is set up and getting first steps towards continuous integration, we have the goal to set up and help developers, scientists, and users to get there to develop a continuous integration strategy. And here on this slide, I've marked 3 important goals of continuous integration or continuous X. The first thing is, if you ask yourself, okay, why should I do those kind of things? Why should I integrate continuous development in my code or in my workflow? First of all, it gives you a kind of quality control, because the new systems currently set up, for example, Eureka, but also other systems, they not only have new architectures like we having set up Intel Ice Lake CPUs, so you have a change from the last generation of Intel CPUs in our case, but in addition to that, Eureka comes with a lot of GPUs. And if you start to develop your code and want to change the architecture, it's important that you have some kind of quality control, because the scientific results shouldn't change there. And the interplay between hardware libraries and application is very sensitive. So if it's also not only for you as a developer or you as an administrator in HPC, it's important that if you change something, if you screw some kind of screws there, that you know what has changed. On the other one hand, you've done some code development, and then something's changed in the scientific result. You want to know where this change comes from the hardware, the library, or the code. And in the end, having a generalized and standardized testing environment also enables you to have a very consequent benchmarking. At every point in your development, you know what performance increase you get if you change the loop or if you change the library you're linking with. And usually a continuous workflow looks like this. The code development starts in a repository, and you've done some changes, you commit your code, and then you trigger a so-called pipeline there. This pipeline could maybe consist of a basic make command. So you integrate, and this step would also only be a make your program. In the next step, you define your testing. This could be, the test could be only, has the make command finished in the correct way, or you can say, okay, I want to make, I want to build, I want to let the executable run and see how the result looks like. If the result is, for example, a none or a 0, then the test fails. And if the result is non-zero, for example, then the test is successful. In the end, if the test of your code development is successful, you have some kind of deployment stage. You can say there are some kind of releases you can signal, you can mark your code milestones, and then after that, you benchmark your stable release, for example. And if you see differences in the benchmarking from one release to another, you can easily compare those benchmarks in the end and have also some kind of feedback. And in this feedback loop, not only you as a developer comes in, but also we are setting up an environment where, for example, performance engineers can also have a look at this specific benchmark and give you feedback on the code development there. And then the cycle starts all over again. At KIT or in general, most of the users come with their own GitLab, but also we provide a GitLab resource at our own. But there are different sources you can start your code versioning on. Some names are already quite common, like GitLab, GitHub, Subversion, but there are multitudes of that. You can also set up your own server and having your Git repository there. The next component would be a CX scheduler. This is could be a basic cron job, or GitLab comes with a more sophisticated scheduler there that checks for some kind of events, for example, a code change or commit. And this scheduler knows what has to be done if a specific action or a specific trigger comes there and triggers a pipeline. It also is able to monitor the jobs, and here also GitLab is, I think, one of the most common examples, but also GitLab, Jenkins, or Python-based BuildBot are different examples where you have an interface and a GUI for those kind of schedulers. But first you have to come with your repository, then you have some kind of overlay scheduler above that. In the end, the runner defines where the job and how the job is performed. So I've mentioned the make command, but also if you submit your code or the executable to the HPC system, here again, you have to execute and monitor jobs, upload the results on a different page. But again, within GitLab, this is a concentrated way where you have GitLab runner integrated. Same comes for GitHub and Jenkins. And BuildBot, you have the host and the worker kind of things going on. But those 3 steps can always be found in continuous integration. And now the challenge for HPC comes into play. Here you see basically an HPC system runs a little bit different than your machine you're locally working on. We have to deal with a dynamic resource allocation because some kind of tests are pretty small, some are more evolved there. But in our view, the user experience should be the same as on your very home and local system. So we try to combine those kind of components there. And I've mentioned the testing. So if you imagine yourself working on the code and you change something, you commit your change. And of course, you don't want to wait 8, 10, 12, or to the next day until you know if the code is broken on the machine. You want to get your result right away. So in the third component, short turnaround times is also important for us, that all the CI and CX pipelines are processed in a very simultaneous and very fast way. And the last point is in security point we've been working on the last year. In many cases and many use cases we've seen, Docker containers are the kind of way most users are working with, but Docker containers need root privileges. And this we can't allow on HPC systems. So at this point, we also had to find a workaround how we can enable this. At KIT, we defined 3 levels of continuous X. The level 1 is basically the same as you would set up a basic cron job on a local partition. Here in this case, this is Eureka, but it can also be another system where all the workers, so the workers get the job from the continuous, for example, from Gitlab, and those jobs are submitted in the basic as a basic Slurm job or batch job in general, and then are executed and can be collected by Gitlab again. But this is in user interactive way. At level 2, this step, the interactive step, is then done by our so-called orchestration servers. And those orchestration servers are dedicated to the HPC system. Very, very short and small jobs can be run on, and longer jobs are submitted in the batch job. This is suitable for medium volume applications or use cases where we have much harder time constraints than to the level 1 application and use case I've mentioned. And level 3, I think, from my point of view here, the fun begins. We have not only CPU and GPUs in the HPC partition and accelerator partition, but also we have a so-called future technologies partition, where different hardware technologies are set in. And this level 3 CX is running on those, or the workers are running on those hardware partitions there. Right now, this is managed by administrators, but in this case, if you have an established workflow and coming with your Git repository, you set up this workflow once, and then you have you can always check your code changes for example, 3 or 4 different hardware architectures, and see how your code changes apply to that, or how your software or your code development is performing on CPUs versus ARM versus GPUs, or different generation of those. Right now on level 3, we have a bandwidth of different architectures, and we are currently extending this. So we plan to have at least 2 new systems coming up each year, or even more. For example, if you think of different development samples. The most recent ones are AMD Rome or Milan and ME100 to have a different environment against in Eureka in the production system. We have NVIDIA A100, and I think it's very important if you think about sustainable software development that you can compare, for example, how your code performs on different architectures. And the last edition there with a completely different setup when it comes to compiler sets are the Fujitsu ARM processors. Here we also provide access to those kind of architecture in level 3. We support containers. So I've mentioned Docker, but also we support natively Singularity. And Docker images are supported as well using en route. So having a custom executor for GitLab runner from our side, you would be able to use your Docker image in our HPC systems. And in the near future, we plan also to incorporate Podman as a third container support to give you more flexibility in that kind of manner. In general, our future plans there is like a better or more, at least more GitLab runner as an executors. So not only incorporating Slurm, but other aspects as well. And I think containers will be a very strong point when it comes to independent work environments. So we strongly enforce our ability to support containers in different kinds of levels of Docker containers and tools there, to also extend our continuous X as a service within NHR and for all the Hoorica users there. And this would be a very rough tour about what we have done so far at KIT.
Thanks a lot. And we can switch to the second part of the presentation. Terry, you should be able to share your slides.
Yes, so let me try. Okay, perfect. So this is of course not just my job. Well, I'm part of a team here at KIT. We have multiple people working on it. Actually, some people are missing because they joined more recently. And we also have external collaborators from University of Tennessee or Valencia. So some of them are present in the call, so they might also be able to answer some questions or contribute to some specific aspects. Maybe, yes, here's better, I think. So we have, so first, what I want here with this talk is to just give a quick overview of what we're doing and try to, let's say, brush a bunch of different aspects and techniques that we're using. So I will not go into details of everything, just really some overview. And I guess if there is technical questions, we can take that to later to the discussions. So just for some context, we're doing a sparse linear algebra library, mostly high performance, of course. And so what we have is sparse linear solvers, a lot of advanced preconditioning techniques. We propose a lot of different linear algebra building blocks, and our library is made so that it's extensible, sustainable. So sustainable software development was at the heart of the library design, which is why we have this sort of image on the right side with a lot of different. So first we have a core library infrastructure with just algorithms, and behind the scenes we have multiple backends for what hardware we are targeting. And very relevant and very important for us are the CUDA, HIP, and DPC++ backends. So CUDA for NVIDIA type of hardware, HIP for AMD type of hardware, and DPC++ for the newer Intel GPUs, which we already are testing and have some working implementation. So we're part of the European project, but also of the eFoice and XSDK American project. We are part of ECP, and we have a lot of different collaborations everywhere. So what I want to say from that is that high performance is very important for us, and that does mean a lot of things in terms of CI. What I want to start to introduce our continuous integration and benchmarking setup with this sort of workflow. So that actually looks a lot like the image that Jennifer had in her slide in the previous presentation. It's really the same sort of technique. She really showed properly the cycle there. And basically what we have is developer pushes some source code to his repository. And what happens concretely in our pipelines, so what you will be seeing later on, is we have multiple steps. Like first of all, we try to build our software so that it works on all the different hardware that we like and we want to use. That keeps increasing also, which is another problem. We want to do testing, of course, of the functionality, like to make sure that our kernels are correct with parallelization and different optimizations. Then we do a lot of different code analysis, so that's nice little helpers, so that we know, for example, if we have good coverage in terms of testing, if we have some bugs which would be easy to fix, this kind of things. Afterwards, we have a code review process, standard GitHub based workflow in that aspect. And when we merge the feature into our main develop branch, some more tests running actually on the systems. So for example, we do memory and thread sanitizer so that we know we did not add critical parallel bugs, for example. Those are more heavy, so that's why we put them here. And then what's interesting for us afterwards is we want to make sure that our performance is, so not only our features are working, but we also want to make sure that they are highly performant. And so we have this sort of block here, which is about continuous benchmarking. So we want to push jobs to HPC system, get some data, which we put in a repository, and afterwards have something to visualize all of that. Yes, so that's sort of the main big overview. I will not discuss the tools in that presentation. I will talk about the different workflows that we have in parallel inside that cycle somewhat. So we are using actually a lot of different CI features for different reasons. So for example, one aspect we are using, and I can recommend people who are on GitHub to use that because it's actually really nice, are the Github Actions. So if you're on GitHub, there is this button here, Actions, which will, if you did not do anything yet, will tell you how to set it up. And by default, you can do a lot of things like building your software on Windows and macOS type of systems. That's really useful because usually we don't have access to such systems in HPC machines, for example. There is no HPC Windows-based platform. So for testing that our software also builds on Windows or macOS, this is really a nice way of doing that. And then we have a lot of nice helpers. That's another way of doing CI, actually. Basically, we have a lot of scripts implemented where we can do nice, useful things like rebasing a pull request on top of the last state, labeling a pull request, or doing code formatting kind of stuff. So there is a bit more things behind the scenes, but that's the main key aspects here with the GitHub Actions, and I think that's actually usually a very nice way to start doing CI without even looking into going on HPC machines and whatnot. So now we also use GitLab, and that's actually our main CI driver. What we're doing is a bit complicated, I guess, and so we have these charts on the side. That's what I want to introduce first. So the first part here is like a quick overview type of CI jobs. So we try to run a bunch of jobs on different hardware that we're interested on and different configurations, so that we know in general the pull request is relatively long. So that's something we are always running. And on the other side, we have a child pipeline, which is actually shown here as well. So that expands to this one. And that one is run only before merging or when we want to test, is everything actually absolutely functional on that pull request. And here, as you can see, we have much more jobs. And particularly much more jobs which run on HPC machines. So it's actually really useful to separate them into those two different aspects. So now I want to go into the details of what the jobs do. So as I said earlier, we have 3 different types of hardware. And for now, the only hardware, the only jobs we are running are the CUDA-based jobs, which we are pushing onto the KT NHRCI setup, which Jennifer presented earlier. So for now, we are only on level 2. And before moving to level 3, as we discussed just before the talk, we need to interact with the admins because that's a very new feature, and we need to make sure that everything will be working for the first time, at least. And then after it's set up, everything will be correct. So for now, we're only running on level 2 here. But as you can see, we have all sorts of different CUDA combination with behind the scenes GCC, CLang, all sorts of compilers. And on the side, we have 2 private machines for now, which we keep using also for other convenient things. One is an AMD machine with some AMD graphic card where we are doing our testing, and which is a red box here. And the blue box here is an Intel system with one of the new discrete GPUs, which we're also using for testing the new DPC++ feature of our software. So that's for the full job. As you can see, for the full job, most of the jobs are running on the HPC system. But for the overview jobs, actually, it's much more evenly spread. Yes, so before actually running things, there is, as you saw earlier, we have a lot of different environments. And what that means is that we need to generate and manage a lot of different containers with different software and combinations, let's say. And that's what I'm showing here. So we have all of those containers. One job here is one container, but we have different steps in the CI pipeline. We use CI for managing our containers. So that's also the same sort of workflow that we saw previously applies to the container generation itself. Not just to our software. And whenever we merge a pull request for changing the containers, this is what happens. So we build the containers with all the different configurations. We test with some simple scripts that everything that should be there is actually in the container. And afterwards, if everything is working, we deploy that. That means we push everything to Docker Hub. So everyone can pull our containers directly publicly. And why we do that is because that's one of the, at least to us, that's one of the useful ways to use en route. So the KT level 2 CI, at least, and possibly level 3 as well, in fact. So this is an overview of which works somewhat. So as I was saying, we have all jobs which are CUDA-based and all also Intel compiler, old Intel compiler jobs which are running on this KT system for now. And in 2 ways asynchronously somewhat. So we have this setup we just saw with the container generation, which pushes containers to Docker Hub. And on the others, our GitLab instance, I mean the main GitLab instance, will push to the GitLab runners we have created on 2 systems. So the ForHLR2 CI node and the BW Unicluster CI node, where we have created a custom GitLab executable, which is end-based. So that's very much what is already provided by the KT CI team. We only slightly modified the en route executor with for our setup, nothing too important. And what this does is it pull and caches the images. That means from Hub, a public image. afterwards, it uses that and transforms it to an en route format somewhat, and from that it instances like launches and gets into the containers themselves. So that's a fairly simple set of scripts actually, but of course you need to make sure that they are properly working. And it's in fact a fairly simple setup, nothing too complicated, I think. So there is a few issues nonetheless, mostly also because of the it's a fairly new feature, at least, and as for us, we moved to that setup maybe 2 weeks ago or something like that. So it's also a very new thing for us. So our current solution, as we saw, is based on Docker container generation. But as Jennifer said, we cannot really use Docker on HPC machines. So for at least for generating the containers, you need to do that somewhere. And for now we do that on one of our machine. But I guess maybe it's better to Singularity, for example, or to try something else that might integrate better onto HPC systems for container management. The aspect is where you store the containers, because you need a registry. So here, for us, that is Docker Hub, which we just saw. But you can have limiting features like you cannot download your container more than a certain number of time over a time period or something like that, except if you pay. So it may be useful to have a registry set up somewhere for user as well, and know if that is planned or available at least. So for now, Docker Hub works for us. But we need to do to work on that a little bit. So another thing is, so that's a bit of details here, but it's somewhat important for the last part. What happens when we are pulling a container from Docker Hub is that it pulls by en route. It pulls the image, and we have like the hash of the different parts of the container that it stores. And then it converts that container to a squashfs image, which is a format that en route likes to use for creating the containers. And from that squashfs, it actually creates a container. And what that means is that we actually have some data management issues somewhat, particularly because we are doing things in parallel as well. So the question is, where should we store all of that on the HPC systems? For now, we have created a project for where we store that, and we use temporary folders quite a lot. But probably some policy need to be defined for this kind of things. So I just said we have the hashed image, which Docker Hub stores so that it does not re-download every single time. Then we have the squashfs files, which we like to store, because then we don't need to try to download every single time if we have the squashfs already available. And we also have the temporary container instance when we are actually creating the container that is also stored somewhere, and that also takes some data. And finally, we have all this thing on the side, which is Ccache. So that's a compiler cache, which allows to store some intermediate compiler information. And that also takes some space, so we also need to store that somewhere. Another final aspect is very much related to the orchestration that we talked about earlier. So we can use the machines in parallel, and the big question is how do we do load balancing, how many parallel jobs do we use, and whatnot. So for now, we have a simple set of environment variables, which we define ourselves for a nice, so that we are nice users, let's say. But again, probably some policies need to be defined there. So maybe these are the 2 points where having standard policies in place might be useful, from my opinion. Data management and parallelism and load management when we accept that multiple users can use the machine at the same time. Right. Then there is a full continuous benchmarking thing. I think I will not go into detail here. So what we want to do is to have, as I said earlier, get some data and visualize that. So we had something working on some HPC machines like Jewels, for example. That was a few years ago, and we had things like this where we automatically create a commit with the reference of what was benchmarked, where all the data, and so on in a standard format. So that makes it very easy to track. And we already had some visualization set up, but we're quite not happy with that. And there are some next steps for pushing that forward. One is to move to the level 1 setup, actually, that Jennifer just presented, which allows to directly submit jobs to the HPC machine and use that for benchmarking, for example. And another one is all the visualization part. So it would be nice to have a dashboard where for every commit we have performance measures and graphs and whatnot, and we can know how much or progressed or improved. And for complex HPC data, we did not find anything directly useful or with a lot of limitations. And so we have a project started by some students, and we are hoping to get something nice out of that. And hopefully that will be useful to other teams as well, who are also doing this kind of setup. So thanks for listening, and I will take questions.
Thank you very much for a nice talk.